Okay. Nowadays I get a voice message. That's amazing. All right. So let me, kind of something which I have been, oh God, I can't once again see my iScribe. I thought I had opened it up. Okay, just 1 second. I have to admit somebody. Yeah. Okay, so just give me a minute, guys. iScribe should be open, yeah. So let's try sharing again. Show Windows. Fine. So the one thing that I had been talking to you guys about is, in the infinitely deep well, suppose you define the potential like this, I mean, the extent of the well, basically. So your V of X is equal to 0 when minus A is less than equal to X is less than equal to A, and is basically infinity otherwise, right? Yeah. So then we do know that the well extent, okay, so just 1 second, somebody else is to be admitted. Yeah. So then we do know that the extent of the well is from minus A to plus A, right? So the length of the well is equal to 2A, correct? And what you will realize is that so our solutions pretty much look the same, right? So if this is your x-axis and this is your minus A position, or rather I should do this by a solid line. Okay, this is your minus A position where your V of X goes off to infinity, and again this is your plus A position, okay, where your V of X again goes off to infinity, and this is essentially your 0 position, which is essentially marking the center of the well. Okay, so this is the center of the well. Now your again your E1 will be essentially somewhere here. Okay, I'm just marking. I can do that because the potential and the energy are essentially, the units are the same. And then you have 2, 3, 4. This is your E2, right? And then 5, 6, 7, 8, 9, and this is your E3. Let's not bother about the others, okay? Now your wave functions look identical, okay? So here, please note, it's going to be like this, correct? Yeah, it is going to be identical in appearance, okay? Then here you have essentially something like this, right? Yeah. So what do I mean by identical? Of course, it's going to 0 at the edges of the well, but the edges of the well now are x is equal to minus A and x is equal to plus A. So essentially what you have to note is about the center of the well, this looks like an even function, correct? This looks like an even function. This looks like an odd function. Okay, actually I should have probably drawn it the other way. This is again like an even function. And what I was telling you last time is that you will find that this will be defined as a cost function. This is a sine function. This again as a cost function, and so on and so forth. Okay. So when that particular problem that I had given you, where the well, what did it look like? If essentially your psi of x0, right, was equal to a, I forget the exact problem now, just 1 second. I should open up that particular PDF. I'm feeling a bit lazy. So let me just write it down. Something which I had picked up from Brandon and Yushin. Yeah. So A, and essentially it was a square minus x square, right? And here, as you realize that your well does extend from minus A to plus A, correct? So essentially, please, you have to be a bit careful and, kind of do your problem, you realizing that your solution is going to alternate between cosine and sine. Okay, as I had told you before, there is a discussion of this in the quantum mechanics book by Griffiths. All right, so you can just go and take a look over there. All right, I should have gotten you the page number, but I forgot. So anyway, doesn't matter, it is there. I can send it over on the WhatsApp group or whatever. All right, if you people need more help in that direction. But this is how you need to work it out. Some of you may have already done it, but Chetan asked this doubt last time, and I just wanted to clarify that this is indeed the case. Okay. So I will stop my share now, and we shall just, I will share once again that particular PDF, right? Oh God, okay, today I've opened too many, what do you call it? All right, guys. Okay, so let me, I don't know, I can't shut a whole bunch of things. All right, just give me a minute. I'm going to actually go ahead and shut a whole bunch of windows because it's showing me things which I actually don't require. Yeah, these two also I think we can just shut. All right, so now let me see if I share. Okay, if I try sharing now, whether I will get the correct set. Okay, still no. Right, okay. Where is that option of getting the other windows? I can't see it. Okay, not my day. Let me see. I wanted essentially, yeah, this is the one. Okay, so let me see if I try sharing now, whether it comes. Ah, there it is. Okay, so if you remember, we were essentially engaged in this particular problem over here, all right, which is the infinitely deep well, which is sitting in a superposition of the first and the of the ground and the first excited state, right? And what we did last time is that we actually normalized the psi x0, and now we have to essentially find out what is psi xt and psi the probability. Okay, so let us start off from this. I hope everybody remembers this problem. Okay, so this is essentially what we are tackling right now, and I will also show you if possible. Okay, I have located the website where you can actually do a simulation of a superposition and see how the probability varies as a function of time. Okay, so just let me yeah, let me, okay, no, sorry. Not my day. All right. Stop the share and we will go back to the ice cream. Okay. Yeah. So, so if you remember what was the basic situation, you are given your psi x0 as equal to a, and then you have the first ground state and the first excited state, right? And our job was first to normalize psi x0. And as I kind of told you, since it's an even mixture, it was fairly simple. We did the whole, working out, but we found that it was essentially going to be nothing but 1 upon root 2, right? Yeah. So thereby, if you now write down your psi x0, which is equal to 1 upon root 2, and then you have, what is it? Root of 2 by, I forget the length of the well. We're taking it, I presume. Did I take it as L or did I take it as A? Please, those of you remember what I took it as A. Okay. So 2A sine, then this will be essentially pi x by A plus root 2 by A, and then you have sine of 2 pi x by A, right? Yeah, so this is basically it. Of course, if you simplify, you will just get a 1 upon root A, And then you'll have essentially these two, right? Sine of pi x by a plus sine of 2 pi x by a. Okay, so this is what you will essentially get. Now let us now do the second thing, which was essentially we were supposed to find out this, correct? And so please note, we are now going to get how the wave function will be as a function of time. Yeah. And then find out what is the probability distribution as a function of time. And this is where things start getting quite interesting. So let me just do that for you. All right. So yeah, try and see if you can also work along with me. Let me just find. Oh, okay. Yeah. So yeah, somewhere here, I think. Okay. All right, so essentially your psi of xt, of course, is going to be nothing but 1 by root a. We can keep that outside. And then we'll have a sine of pi x by a. And then you'll have an e to the power of minus I by h cross. And then you'll have your E1, which is over here, h cross square pi square by 2ma square, correct, times t, right? And then you'll have a plus sine of 2 pi x by a. Okay, and I'm going to write down the time dependent part here, minus I by h cross. This I think I did write down last time itself, but doesn't matter. 4h cross square pi square by 2m a square, correct, t. Okay, so essentially you have this, right? Now what do you have to do? You essentially have to find out the probability distribution as a function of time. So let's try doing that. So what do you need for that? You basically need psi xt, right? So which is going to be, of course, your psi star xt into psi xt. Now, what you will realize is that the time component would vanish if the system was in a pure state, okay? In a single stationary state. Yeah, that's why they're called stationary states. However, if it is in a mixture of stationary states, it's not a stationary affair, okay? So that is the interesting thing, as I said, you know, which we haven't really encountered as a part of our normal quantum mechanics class, which we are going to see over here. So I'm going to be a little careful and change the page. Otherwise, I will be overwriting on things. Yeah. So let us now write down what is going to be your psi star xt. Yeah. And that is going to be nothing but 1 upon root a. And here you will have essentially your sine of n. Sorry, I don't know why I wrote n. Okay, so it will be pi x by a. And then you have e to the power of I by h cross. Okay, so the I goes to minus I, right? Now what's happened over here? I have lost my page. 1 second, guys. Yeah. No, I haven't lost my page. I don't know what I'm doing. So you have essentially a minus I by h cross. And then, of course, you have your I don't know what I've done here. Yeah, doesn't matter. H cross square pi square by 2ma square t, correct? Plus you will have sine of uh, 2 pi x by a into e to the power of I by h cross 4h cross square pi square by 2ma square t. And then, of course, you're going to be multiplying it by, of course, you'll have a 1 upon root a again. And then you will have your wave function, right? By a e to the power of I by, so this you will have a minus sign, sorry, h cross square pi square by 2ma square t plus sine of 2 pi x by a e to the power of minus.
My left hand side.
Sorry?
On the left hand side is not
Oh,
psi
yeah, yeah.
square, it
I'm
says.
sorry. I'm sorry. I'm sorry. Yeah, you're absolutely right. I should have. Okay. I'm already doing psi xt. Okay. I'm very sorry. Yeah, I meant to write just the, what do you call, the psi star, but I ended up writing both. All right. So, yeah. So, thank you. Thank you for pointing that out. All right. So, what will we get now? We'll get a 1 upon a, and then just multiply the terms. So you will get, of course, a sine square pi x by a. Okay, so this is going to be the first term into the very first term on the second set. All right, and then you will get sine pi x by a. Okay, into sine 2 pi x by a. And now you're going to get a time dependent term. So you will get e to the power of, let's say, I by h cross. And you will get now, you will get essentially, there is 4 here and there's 3 here. So you'll get a, let me just write it down, minus 3 h cross square pi square by 2 m a square t. Am I right? Yeah. So this is what you're going to get. Plus, of course, you will get now sine, you can of course write it both ways, 2 pi x by a into sine pi x by a. And then you'll get into e to the power of, you will get exactly the same thing again, all right? So you'll get over here. So that was first into this. Yeah, here you'll get e to the power of, sorry, you'll get I by h cross into 3 h cross square pi square by 2 m a square t. Okay, so you will get, for one, you will get the exponent as negative, the other you will get the exponent as positive, right? And then of course your last term is going to be just a sine square of uh, 2 pi x by a. So have I done it correctly, guys? I hope I have. Anybody? Any comments? Is this correct? Okay, thank you. So now what do we do over here? So we have essentially a 1 by a. And now let's just write it down a little more neatly. So this is going to be your mod psi xt whole square. This is going to be 1 upon a. And then you have essentially your sine square pi x by a. I'm going to write down the last term also, the sine square 2 pi x by a. And then what do you have? You have a plus sine of pi x by a into a sine of 2 pi x by a. And then you have e to the power of, okay, I by h cross. And then you have 3 h cross square pi square by 2 m a square, okay, t plus e to the power of minus I by h cross. And then, oh, I don't have space, 3 h cross square pi square by 2 m a square t. I hope it can be seen, all right? And then you of course have to draw a big bracket here, all right? I hope it can be seen, okay? Or maybe it's run over the t, I don't know, okay. So this is basically what it is. Sorry, I have to admit somebody. So this, so please note what we can do now, okay, is we can probably write this up, okay, again, this part, okay. So it is going to be essentially you can write this as a what is it? E to the power of I theta plus e to the power of minus I theta. What do you get? Okay.
2 cos.
2 cos theta, is it? Yeah. So this is essentially cos theta plus I sine theta, right? And then e to the power of minus I theta is again cos theta minus I sine theta. So essentially, if you add the two, you should get a 2 cos theta, right? So e to the power I theta plus e to the power of minus I theta. All right. Yeah. So now we can do that. So therefore, your psi xt mod square will be essentially nothing but 1 by a. And now this is a constant, this is a time independent thing that you get, right? Plus a sine square 2 pi x by a. And on this is riding a time dependent term, right? Which is essentially your sine of pi x by a, sine of 2 pi x by a. There will be, of course, a 2 over here. And then you have a cosine of how much? Essentially 3 h cross square pi square by 2 m a square, okay, into, I would say, t by, there should be an h cross. Am I right? Yeah, this is what you will get. So I should have put this as a curly bracket. Am I right? Okay. So what you will see is now there is a time cosine, time dependent term, which is now coming in. Okay. Yeah. So the point is that, of course, if you kind of average it over time, all right, you will find that you will get your, you're going to get back to your original values. Essentially, you will just get these, correct? This guy is going to, the third term is going to essentially average out over time, okay? You do it over several cycles of oscillations. However, the truth is that it will oscillate, okay? And what is the oscillation frequency related to? You can see it is related to the energy difference between the two states, okay? So essentially, what is the difference over here, since it is the energies of the ground state and the first excited state? It is essentially 3E1, which is basically relevant over here. So the frequency is 3E1 by H cross. That is the frequency of oscillation of the probability. All right. So let me just try and show you one particular simulation. I'm going to stop this share. Let me see if I'm able to at all share that or not. Okay. So maybe I need to go here to okay, is this visible to people? Can you see superposition states in an infinite square well?
Yes, ma'am.
Yes, you are able to see it, right? So are you able to see this graph over here, please? Yeah, on the left-hand side?
Yes, ma'am.
Okay, so now look at it over here. What is the quantum state? The quantum state essentially, this is your ground eigenstate, correct? Ground state of the Hamiltonian, correct? What you have solved from your Schrodinger equation. And this is the first excited state. So what I can do, if you look over here, I can make the contribution fully from the ground state. And this is the wave function that you are all used to, correct? Does this make sense, guys?
Yes, ma'am.
Huh? Now I can make it completely here. Okay, so that means psi is equal to psi 2, all right, which is completely the first excited state. And you people know this probability distribution as well, correct? Is this all right?
Yes, ma'am.
Okay, so now what I'm going to do, the problem that we have been solving, we are going to do half and half. So you can see root of 5 by 10, which is 1 by root 2 actually, plus 1 by root 2. This is what we did. Correct, guys? Yeah. So now look at it, how this probability distribution is actually changing with time. Okay. And what is the frequency of change? Please remember, it is nothing but the energy differential divided by h cross. That gives you your omega. Is this clear? All right. Now, suppose I want to also find out the probability, the position, expectation value of the position. Look at how it is changing. That's your dotted line. All right. So that gives you the change in the how the expectation value of the position is actually oscillating. And now you can also do an uncertainty with respect to the position. Okay. Naturally, the uncertainty seems to widen when you have a more flatter distribution. If it is peaked, on the other hand, the uncertainty reduces, right? Okay, so please, so it's a pretty interesting graph. So let's try for some other superpositions, all right? So this is half and half. So let's now make it leaning more towards the first excited state. Okay, I give a heavier weightage and see what happens now. Okay. So I've given basically root of 2 by 10 for the ground state and root of 8 by 10 for the first excited state. Let's try moving it the other way. Okay, so a more heavy weight towards the ground state. Okay, you can see how it looks now. Okay, so the wave mostly looks like the ground state with a marginal amount of, alteration. Whereas on the other side, if you look at it, looks mostly like the, what do you call it? The first excited state, but there is an oscillation, correct? Yeah. Now, let us try, instead of doing this, let me go to this and let's try this. First, the ground state and the second excited state. Okay, so all of you try and remember how the wave function looks for the second excited state. You have essentially two nodes, correct? Yeah, and you have three bumps, right? So three places where the probability of finding the particle is the most. So this is, of course, the contribution from just the ground state. This is the contribution just from the second excited state. This is exactly what I was telling you. Two nodes and three peaks, right? Yeah. Now let's do a half and half contribution. Okay. And what you can see is the frequency of change is much higher. And why is that? Because it depends upon the energy differential between the two states, correct? And the energy differential of the between the second excited state and the ground state is obviously higher. Yeah. So this is what you will get. Now, if I make it more towards the second excited state, you will see that it looks mostly like the second excited state, except that, of course, there is an oscillation. Let's push it more towards the ground state. And you will see that there are certain lobes, but the central guy, okay, is dominant, correct? Which is what the case is for the ground state. You can, of course, make matters more complicated by going to a combination of the second and the first excited state and the second excited state. Let's do a half-half contribution and you can see how it is. It's really, really quite something. Yeah. And of course, you can then try seeing the expectation value of the position. Yeah. And what about the uncertainty? All right. Yeah. So this is a really interesting simulation. I will, I had lost this last time. So I can try and send you this website. Okay. So all of you can just have a look at it because see, we don't do this, as I say, in class. Okay. It's a part of your regular quantum mechanics course, but it should be done. All right. And you guys should get more comfortable with the idea about how things change. Okay. So we can go back again to the first and second, the ground state and the first excited state. And this is essentially the situation that we are looking at. Okay. Any questions, any doubts? Yes, no? You've all gone to sleep. I was looking at the simulation. Yeah.
Can you show the uncertainty again for psi 2 as well as psi 1 for comparison?
Okay, you want to see it for just psi 1? All right. Okay, so let's just
Yes,
go for
ma'am.
the ground state. Let's see the expectation value of the position. It's L by 2, as you can see, correct? And
Yes,
let's try the uncertainty. This is what the uncertainty is, okay? And it's all fixed. Nothing is changing with time. All right. Let's
yes, ma'am.
try making this completely the second state. This is what you get.
Uncertainty.
Yeah.
It became somewhat larger.
Yeah. Because you know that the further you go away from the, what do you call, the ground state, yeah, your essentially the uncertainty will become larger, right? Your ground state is closest to the uncertainty limit. Okay, so keep that in mind. It also will, strictly apply to the position. All right. So now let's try it for the let's try it for the, you can see this is a situation when you go to the second excited state. All right. So this is the expectation value of the position. And this is what I've told, we kind of found out, right, in the last class, that the expectation value of the position is the center of the well. It doesn't matter. Okay. For a stationary state, it is always the center of the well. But the uncertainty is going on increasing. Okay. Because as you can well imagine, there is a high probability of finding the particle here or the particle here. Okay. Not just here. So obviously the uncertainty will keep on increasing. And yes, you should actually now think in terms of how it is going to compare with the classical harmonic oscillator. Okay, so we will actually, you can think about it when you have increasing width, how it is going to be. Okay, so the uncertainty will become large, huge. Okay, right. So anything else you want to see
Yes.
right now? I will share this site with you. Okay, all of you. I will try and share it with you. So you can just play around and do what you want. Okay, it's a pretty interesting one, and I think all of you should have the freedom to really play around with it. Is this okay, everybody?
Yes, ma'am.
Shall I stop the share now? Oh,
Okay.
fine. Yeah. So this is what we have now. Let's try and see what we get as the expectation value of the position. Now, as you saw in that particular simulation, okay, the expectation value of the position is also going to be now changing, correct? Yeah. So there is a change in the, so there is a time dependence. Okay. Now, how do you get back to, what you would, you would have gotten earlier is basically you do, an averaging over cycles, I would say, of oscillations. All right. So over long times, you will end up getting the same measurements, but there is an oscillation that happens. So let's calculate the expectation with respect to expectation value of the position. So let me share my scribe once again. Yeah, all of you can just start doing it. Okay. I am a slow coach here. So people who are, faster at these kind of calculations, just go ahead and do it. And we can just compare answers. Okay. So our third part of the problem, if you remember, was essentially to figure out what was the expectation value of the position. And that, is going to be nothing but your psi star xt x and then psi xt. And then, of course, you would have to integrate the whole thing from 0 to a dx. All right. So go ahead and put down what is your, now you have a pretty big, nasty expression for this. So let me write it down. You have a 1 upon root a sine of pi x by a e to the power of I by h cross h cross square pi square by 2 m a square t, correct, plus 1 by root a. Yeah, I forgot to put the integral in the beginning. Sorry about that. see, there should be an integral from 0 to a over here. This whole thing multiplied by x multiplied by okay, there'll be a dx also, which I'm putting right at the bottom here. Not good. Okay, it doesn't even show. Fine. I hope you guys be able to do a better job of writing the integral than I did. Okay, made a real hash of it. But anyway, I will tell you what I got as the final answer.
Ma'am.
Yeah.
Ma'am,
Yeah.
isn't the integral just the integral of x and psi square dx, ma'am?
See, there will be a time dependent part, correct? Yeah. So it will be x square sine square x, but you will get a sine n pi a by x into sine 2 pi a, okay, into e to the power of I by h cross. You'll have the energy differential into time. Okay, so that's going to be there. Okay, so you're going to, so just let me write it down and you see whether, you get the same thing. So I'm going to get essentially this. I will have a 1 by a, which will come out. Okay, so I'm just writing it down. See whether you get the same thing. So you'll get essentially 3 integrals. One is this, which is exactly what, you were saying. Pi x by a dx. Okay, you get this integral. Then you will get one more integral. So 2 more integrals. One is this. Then you'll get essentially e to the power of, I'm going to write it a little concisely. I will write it IH cross. I'm going to write it as 3E1. Okay, I hope everybody understands what 3E1 is. E1 being the ground state energy. Yeah.
Ma'am, did you hear me say it as psi or sine, ma'am?
I have to confess, I don't know what I heard exactly. I'm not able to recall it at the moment. What did you say?
In the previous page, you wrote out, you expanded the whole expression for psi star
Correct.
x and psi, no, ma'am.
Correct.
I suggested, why don't you write it as x into psi, wave function psi square?
I see.
The one that you calculated in the previous step.
Yes, you could do that. You'll have to do the integration again, no, Nitin?
Ma'am, I didn't get that. It broke.
So the point is, you wanted me to take the expression which I had of psi x square, right? Isn't it?
Yes,
and multiplied
yes,
by x and then do an integration.
Yes, ma'am.
Yeah, you're absolutely right. I could have done it from there, but it's basically, I'm just trying to get more steps in so that it's clear to everybody. Okay, of course, that would be the correct thing to do. Yeah, as long as you put
I
in
thought both were different things to do, ma'am.
No, they aren't different. They aren't different. They can't be, no? Yeah, you have to just do the integration correctly. That's all. I think I missed an x over here. I'm sorry. In the second integral, I have missed an x, guys. There has to be an x over here. Okay, they are not different. You're absolutely right. Put in the x and put the integration and you're home. Okay, I just didn't want to do a quick a more hodgepodge thing. That's not how I operate. Okay? People do that and they don't make mistakes. I unfortunately make mistakes. So I don't do it like that. If you can do it, please, okay? Cut steps. All right. What Nitin is saying is absolutely right. Time is at premium. So kindly, do things fast As in how, as long as you don't make mistakes, it's fine. But since I'm teaching you guys, I'm just doing the whole lot. Okay, that's all. So that's it. Okay, so now basically you have to calculate these three integrals. Okay, this first integral, this integral here, and this integral. So I really heard it as sine square, I think, not as sine square, what you said. Okay, so that's pretty much it. So I'm sorry if I kind of confused you. Okay, so I will just tell you what I got as the various integrals. Okay. So just try and do it, guys, and see whether you're getting the same answers as me. Okay. This is what I got for I1. For I3, again, you will get exactly the same. You'll essentially get your a square x 4. And your I2 is going to be a time dependent one. Okay. So this you're going to get this is at least what I got. You guys see what you get. Okay, this is what I essentially got. Okay, and just to make it kind of clear, I'll put it as 3 1 divided by x. Sorry, I shouldn't get an a square here. I should just So just pay attention, please, all of you. I know it's not so easy to get these integrals so fast, but what I want you to pay attention to is the final answer, all of you. Do I have your attention, please, everybody?
Yes, ma'am.
Okay, cool. So what I want you to see is that you can see that essentially the solution, okay, is oscillating. By oscillating, of course, I mean in the time, Okay, all right, oscillating about the value of A by 2. Okay, so A by 2, of course, is the expectation value of the system at, when it's a stationary state, right? Any stationary state, your expectation value of the position is always A by 2. Okay, so here now, since there is a mixture of two stationary states, you're going to still have the mean of the, the oscillations will happen about A by 2. All right. Now, what is the frequency of the oscillation? It is nothing but the mixture of the two states that you took, E2 minus E1, okay? That divided by H cross is essentially going to give you the omega of the oscillation. What about the amplitude? The amplitude, please note, is 16 by 9 pi square into A, okay? And how much is this value? I have just kind of put in things and just figured out it's about 0.368. Okay, so that is what you're going to get. Now you can well imagine that as and how you do a mixture of, let's say, the first and the ground state and the second excited state, this amplitude is actually going to go larger and larger. So this is actually a kind of good idea to keep in your head so that anytime you're given a problem, you know how to actually attack it. Okay. Any doubts, please? Any clarifications required? Is the solution kind of sitting well with you guys? Because if there are issues, yeah, tell me, Chetan.
16 by 9 pi square, is it, ma'am?
That's what I got, at least. Yeah, I may be wrong, okay? I mean, so there has to be an oscillation. It seemed to me that this 0.36A was quite all right. So I kind of left it there and didn't check my solution, but that's what I got. Yeah, 16 by 9 pi square.
Okay. Then it should be 0.18A.
Is it? Okay, maybe I made a mistake. I'll have a look, okay? Thanks. Let me point it out, okay? So this is something you think that there may be an issue with. Okay, I'll check it out. Okay, I don't have my calculator here, so I'll do that, okay? Yeah, it looks a bit large. I agree with you. Okay, yeah. Fine. Any, so anything, so I think what Chetan says is right. It's, I think, 0.188 because as I can see, pi is around 3, okay, very vaguely. 3 into 3 is going to be 9, 9 into 9 is 81. 16 by 81 is not, 16 is not like 1/3 of 81. Yeah, so more like, yeah, I think 0.188 is sounds more correct. Okay. Fine. So just let's just I'm going to stop the share and let's just get back to what were the other bits of this problem. And I kind of told you how we can try and do that next, earlier. But let me just repeat it. So please note, we have computed X and you can also do its angular frequency and oscillation. And you know how it can be done, right? Yeah. So amplitude of oscillation, angular frequency, we just discussed this. You can compute now the expectation value of the momentum. Please go ahead and use Ehrenfest theorem. And now please remember, you're going to be oscillating about 0, correct? Yeah, because, so let me see what I essentially got. Yeah, you will get essentially just an oscillation in time and you will realize that that is going to be about the mean value of 0, okay? So there is going to be an oscillation about 0. And I, of course, talked about this last part of the problem where you were asked whether if one measured the energy, what one value would one get, and to find the expectation value of the Hamiltonian and how would this compare to E1 and E2. And we talked about it last time and I have told you that the only values that you can measure is essentially an eigenvalue. So you're obviously going to, if you kind of, the system is prepared, several identical systems are prepared in this state, Every time you make a measurement, you will either measure E1 or you will measure E2. But then if you measure for an infinite number of systems, you will find that you're going to get the E1 and E2 values in equal probability. So thereby your expectation value of the Hamiltonian is just going to be an average of E1 and E2. Okay. So it's E1 plus E2 divided by 2. In which case, in this case, of course, you know that E1 E2 is essentially 4 times E1. So you will get 5 E1 by 2. Okay, that's going to be an expectation value of the Hamiltonian. And you can compare, when you compare it with E1 and E2, of course, it's going to be the average of the two. You can, of course, go ahead and actually do the calculation of the expectation value using the Hamiltonian. You can go and do that. Okay. The interesting thing will be that, you know, you will find that you don't get a time dependence. Okay, so that's the neat part of the whole business. Go ahead and try and do that. Okay, so now any doubts, please, in this final problem? We have kind of run through from you know, the D and E. We discussed it last time, so I'm not bothering to go into more details over it now. So is everybody good with this?
Yes, ma'am.
Okay. So let me stop the share and I will share something else with you. And these are essentially the set of problems. Oh boy, I can't see it again. All right. So let me, 1 second, right? Let me, I don't know how to handle this. You would think that by doing Zoom so often, I would know how to handle various things. Ah, yeah, here it is. Okay, go down. At least I'm happy that I could show you the animation today. All right, so yeah. So I think this I have uploaded on the drive, okay, the folder on the drive, which I have the link I've shared with you. So has anybody seen this? Have people seen this already?
No, ma'am.
Okay, fine. So it is there, okay? It is called, I think, QM square well additional problems or something like that, all right? So I will just, you know, kind of talk to you about each of these. So let's have a look at the first problem. It says an electron is contained in a one-dimensional box of width 2 angstroms. Calculate its minimum possible energy. Okay, so this I think should be trivial. It is just, you know, you have dimensions and things of that given. But, you know, it has to be the ground state energy of a infinitely deep well, which is of width 2 angstrom. So just calculate the ground state energy. Okay, so that shouldn't be a problem. Let's have a look at the second one. Now this over here, you can see that you have been given that this phi1 and phi2 are the ground and excited states of a particle in an infinitely deep well of width L. All right, and what have you been asked to do? You've been asked to find out the expectation value of the position square. Okay, that's all you've been asked. But these for the state is essentially a superposition. And please look over here, it's not an even superposition, okay? So 1 upon root 5 plus 2 upon root 5 is given. Now, whenever you're given such a kind of a wave function, the first thing that you need to do is basically make sure that it is normalized. Okay, is this clear, everybody? Yeah, it may not be evident, but just check once that this is normalized. This is actually normalized. Okay, this guy is actually normalized. But sometimes, okay, in certain problems, they do not give you normalized wave functions, in which case it makes sense to take a little time to just make sure it is normalized. Okay, so here what you can do is you can just, you know, whatever the weight factors are, just square them. So here it is 1. So 1 square plus 2 square, which is 4, which will be 5 and root of that. Okay, so it is root 5 and you can see it is divided by root 5. So you know it's normalized. So take that few seconds to make sure that it is normalized. All right. And then we have, of course, done this before. You know the form of the ground and the first excited state. So please go ahead and find out what is x square. Okay, so you'll have to essentially carry out integrations, right? Yeah, so it shouldn't be a problem. So this you can do, I think. Now, what about here? Again, a similar problem. You have again a mixture of the first and the ground state and the excited state. Here it is an even mixture. All right. And what have you been asked to do? You have been asked to find the uncertainty in the momentum. I think you can do this again. All right. Uncertainty in the momentum. Please note, you'll have to do what? You'll have to find the expectation value of the momentum. You already know what that is, correct? You have to find the expectation value of the momentum square, all right? And then calculate what is the uncertainty. All right, so I think this is again a problem. It's an extension of what we have already done. So kindly go ahead and do it. Now this problem here, all right, over here, I haven't actually tried solving this, but I think it can be done, all right? You basically are being asked to find out the expectation value, all right, of the, in one of the stationary states, in the nth stationary state of p square m, right? So anyway, you can ignore the px. We know it's a one-dimensional affair, so there's no need to worry about that. Into 2m, okay, where m is of course an integer, all right, and prove that it is actually this. Okay, so this is, it'll kind of help you guys. I will just, check once whether this P has been in some sense altered from the normal Px that we know. Okay, I will just ensure that that is indeed the case, in which case, please expect an addenda to this fourth problem. All right, yeah. Now let's come here to your fifth problem. Okay, and please note here you are given essentially a wave function, and here you have been given it in terms of the exponential functions. All right, yeah. And what has been asked is actually, so kindly don't get totally rattled. All right, what you have been just asked is what is the wave function at a particular time, okay, t. All right, so at t0 it is equal to this, t is equal to 0. So basically you have to find out what it is at a particular time t, all right? So what you have to do is, if this is psi x0, remember how you have found out how it is going to be at psi xt, right? Yeah, by, how do you do it? Remember your way of finding the CNs, correct? Yeah, and then once you have the CNs and you have found the time dependence, you basically replace the time and you can do it. I don't again know how long this will take because both these problems I actually haven't solved. All right. So just give it a shot. If there are any issues, let me know. I will try and do it myself. Okay. Now, what about this? This is again a deep square well, which is extending it from 0 to L. And again, you have a wave function over here, okay, which has been given. What is the probability that the energy of the particle is found to be this particular thing? Okay, h cross square pi square by 2ml square. And you will realize this is the energy of the ground state, correct? So what are you actually supposed to do over here? You're supposed to find out, this is of course, you should be able to expand it as a linear combination of the energy eigenstates, right? And what you have to do is to find out what is the weight factor for the ground state. Square of the mod square of that will give you this probability. Okay, it can be done. Okay, this I think I have done. All right, it can be done. So you should be able to do it. All right. So the important thing is to identify that this is the ground state energy, correct, of the infinitely deep well. All right, and then try and see what you will get as the Cn of the ground state. Okay, that is all that is required. Okay, so try and remember what is the procedure for doing that. Have a look at the last problem. All right, this is an interesting one. It says a particle is moving in an infinitely deep one-dimensional well. All right, at a certain time when the particle is in the ground state of this potential, the wall at x is equal to L is shifted to x is equal to 4L. All right. Calculate the probability of finding the particle in the first excited state. Now, what has been done? You have a particle in an infinitely deep well, which is of dimension L. And it is sitting in the ground state. What is being done now is that this well is suddenly expanded to 4L. Okay. So now what is going to happen is that basically this is like a sudden approximation. Your wave function doesn't change. Your wave function continues to be in the ground state of which one? When the well was only L, or width L. But now it is of course changed to 4L, and the eigenstates are going to be for the well which is of width 4L. So what you have to do is you have to take that wave function, which is the ground state at the width L, and expand it in terms of the eigenfunctions for when the well is 4L in width. Okay. And then find out what is the probability that it is going to be the first excited state of the well, which is 4L in width. Think about it. In case there are doubts, okay, if we are having problems with this, we will take them up. I will assign a particular slot and we will take them up. So any issues, any doubts, any overarching problems? Because I think I've already run over my time. So I should stop now. But if there are any overarching problems, please ask and we can try and get it cleared up. Any issues, please? Okay, so in the next class, whenever that is, we will basically start off with the linear harmonic oscillator. Okay, so I will try and do all the problems. I will give you first of all an overview of linear harmonic oscillators, and then we will try and start solving. So far we have finished off the free particle, and we have finished off the infinitely deep well, infinitely deep square well in class. And now we will move on to the simple harmonic oscillator. Is that all right? Everybody good?
Yes, ma'am.
Yes, ma'am.
Okay, fine. All right. So please start attempting this particular assignment as well. And some few classes down the line, we can just take it up and I can send you the solutions. And if you find that solutions means I will send you the answers. I've discussed the way of doing it now. And if there are any issues, we can take it up in one of the classes. Okay. Yeah. So fine then, I will stop the recording. Oh.